You could just take a camera and tape it.
Yeah, but that's too much work for me. I just want to be able to like upload. I just want to save.
I'll wear the work.
I'm like,
and
I'm
then
not.
I'll send you the videos of me doing the lesson. I mean, it's per time. And sound.
Yeah, but is there a limit or anything?
No,
But then if I go to the movie,
No, a limit on how much time you can record.
I've done it for like, Mr. Wander's done it for like a good 30 minutes.
Okay.
Yeah, he uses it on.
All right, I'll look into it. Okay, here we go. 3 different graphs, but they all have the same limit in the end. So here's a rational function, x squared minus 1 over x minus 1. This is one that, like if we were to reduce it, we would have a hole in the graph, a removable discontinuity. So that's fine, no, because from the left and the right, the limit, right, from the left, from the right, we still have that same limit of 2. Remember, our limits are the y values, but we look at the graph from the left and the right. So the next one, same thing, from the left, from the right. So I don't really care about this point here. It's not important. Okay. With limits, it doesn't matter if the point exists or doesn't exist. It just matters the part right before you get to that point.
What would this be called? I know the other ones are removable discontinuity.
This is also a removable discontinuity. We will need to know those definitions, but I'll get to that point. These are both considered removable. This one and this one are both considered removable. Anytime you have a hole in the graph, it's removable. And then this one is continuous, and there's nothing to suggest that the limit wouldn't be 2. There's a point there. It's approaching from the left and the right, the same y value. So that's why they're all equal to 2. Questions on that? Okay. Okay, we're going to get 2 really basic limits. The limit of k as x approaches c is equal to k. Why is that true? Well, think about this. Let's look at our example here. I'm looking at the equation y equals 3. Remember, whatever we're taking the limit of is a function. That's what we're considering. So when it just says 3, we're really thinking y equals 3. Well, what does y equals 3 look like? This is a horizontal line. So if I have a horizontal line, right, here's my y equals 3, and I want to approach 2 from the left and 2 from the right. Does it matter? No. It's still going to be 3. So I could have any number in here. I could put pi. I could put 1,000,000. Whenever this is a constant, the limit has to be that constant because that is the y value. Good? Okay, next one. This is the limit of x as x approaches c is c. So this is the identity function, which looks like this, right? Y equals x. So if I'm considering my example, right, as x approaches 3, here and here, my y value has to be 3. Any questions? So these are properties of limits. I'm not going to go through in too much detail. I just want you to know what this represents. It's as if you have the sum of 2 things and the limit's out in front, you can separate it and do the limit of each part. Okay? Or you can, if you have the product, like if you have something really complicated and you can separate it into two separate limits and just do each of those and then multiply, that's what that means. Same thing for quotient, like if you have a numerator and denominator and you want to just do each part separate, that's fine. Power rule, same thing. Okay, these are just 2 more examples. I don't know why I have B. I should have changed that, but it's the same problem. Okay, what's I didn't realize I had that same one. Oh well. What's A? Pi. And of course, remember, this is the equation y equals pi.
Oh, yeah, it's a constant.
So it's a constant. Good? And this one has to be 3. All right. Polynomials and rational functions. So far, you've done some of this from last year. So, and I believe you went through some of this also. So basically with a polynomial function, are there any discontinuities? Are there any asymptotes? Anything surprises? Polynomials are just nice, smooth, continuous curves. So to find the limit, I just plug in what I'm approaching. So if it says approaching 2 here, I get to just plug in 2. So it's just 2 squared plus 3 times 2 minus 4. And we get 6. So polynomials, we just plug it in. Now, if we have a rational function, we can just plug in as long as the denominator is not 0. So right here where it says g of c not equal to 0, so denominator can't be equal to 0 if we try to plug it in. If it is equal to 0, then we have to do a little bit of algebra. So in this case, can we just plug in -2? Okay. So we plug in -2 to the top and -2 to the bottom, and we get -1/4. Good. Questions? Okay. I'm not going to worry about the support graphically for right now. Let's just find the limit by substitution. Graphically would mean you just graph it and look. And it's a polynomial, so for that first one. What do we get? What is it? 8 minus 4 is, I know, real tough mental math here.
It's too early for 4.
8 minus 4. Okay.
6.
That's tough. Okay. How about the next one?
1.
Oh, no, that's messy.
1.
It's just 1?
Yeah.
So I have 2 minus 7.
2 minus 7.
Yeah.
Plus
4
5.
over 4. Yeah, I see it. 1? Do I need to show my work?
No.
Okay,
Don't
thanks.
ever do the right.
Jared, my pen's not working at the moment.
Remember,
We don't waste time in calculus.
The top row of calculus.
Don't waste time.
I surrender.
Sometimes it's necessary, and sometimes I'm okay with, like I wouldn't really use anything for those. And actually, I'm going to just go through these algebraically, and then we can look at them graphically. I know it's the direction to say it backwards, but right now I'm more interested in the algebraically. Everybody can graph on their calculator and look at it. It's the algebraically that I'm more concerned with. So the first one, for A, what happens when I go to plug in 2? Okay, so I get 0 on the bottom. Do I get 0 on the top also?
Yeah.
Okay, so what I want to do is I want to, and here's where I always get the question, do I have to keep writing the limit? The answer is yes. You have to keep writing the limit until you've actually plugged it in. Technically, you can't just drop that limit until, because that's what you're doing to that whole thing. Okay. I know it might be a pain to keep writing it. So what do we get? T minus 2, T minus 1, and then T. Perfect. Now, because we're talking limits, I don't care what happens right at 2. And in this case, it actually turns out to be a removable discontinuity, but that has no effect on my limit. So I can just cancel it. Now can I apply the limit? Yes. So we plug in 2, and we get 1/4. How about B? Right, so we have the same situation where we have a 0 on the bottom and then also 0 on the top. We're more concerned about the 0 on the bottom, so we have to do what?
Well, first, figure out the top.
It depends on there's different approaches. I would take the top. So maybe multiply this by 2 over 2, and this by 2 plus x over 2 plus x. Is that okay? I'm going to leave the x on the bottom alone for the moment. So I'll write this limit as x goes to 0. So I have 2 over 2 plus x minus 2 plus x. Oh, oops, there's a 2 times, yeah. Yeah, I'm going to distribute. So whether you, maybe you skip steps. I'm showing lots of steps right now, but yeah, when I go ahead and write this out, I need to distribute. So I really have 2 minus x, so I have a negative x in the top. Oh, we are okay with that? So negative x, and then I have 2 times 2 plus x in the bottom. Now divided by x is the same as multiplying by 1 over x, right? If I were to divide by 2, it's the same as multiplying by 1/2. Why would I rewrite it that way? I hope it's obvious, but do you see it? So now I'm able to cancel, and I'm left with just a negative 1 in the numerator. Good. So let's do that. And now can I plug in?
Yeah.
Yes. Okay, our whole goal was to get rid of that x on the bottom. So I still have a negative 1 in the top, and in the bottom we get 4. Yes. So negative 1, 4.
If we keep all of our limits in a line, we can do it once. Or do we have to write out a little bit of that?
Is it that hard to write?
It is when you're in a full body test on
What's that? Here?
It was just negative x down to the last part.
Yeah, that's all I did there.
And then you multiply this.
Yeah. Okay. Okay, 1 and 2-sided limits. Let me just see how much more we have. Okay, so let's go through these 2 pages and then we'll do a quick little break and then we'll do 2.2. So 1 and 2-sided limits. We know if there's a little plus sign, right? That's the limit from the right. And sometimes it confuses students because it's from the right, but you're kind of moving left, right? And it's the minus is from the left, but you're moving closer to that location, right? Now, how do we know if it has a limit? Right here. F of x has a limit only if the right and the left hand are equal. So this is important. Sometimes you'll see on the free response an AP question will say, does the limit exist? Show work to support. So you would go and you would actually just write in the limit from the left and the limit from the right are equal to the same value. Therefore, you could see that kind of question on the free response. Well, usually free response has like 4 parts to it, like A through D, and this might be part A. That's how it works. They break it. There's always C or like parts A through C or parts A through D. Usually A through D on the free response. But like I said, we will have plenty of practice with that stuff. You guys will be prepared. I hope. I'll do what I can to make you prepared. How's that? Okay, so on this graph, let's go through and just look at the left and the right hand limits. So 0 from the left. Okay, now be careful. We're looking at x equals 0. Well, here's x equals 0. So I'm actually looking at this graph. Yes, from the left is right there. It's 5.
Also 5. And then 5 again.
Okay, from the right, oops, also 5. So therefore, since these two are equal, then we know that one is 5. So just in case, so to verify, you got to show from the left and the right are the same. Okay, how about negative 3 from the left? So right here is my x value of negative 3. So from the left, it's 0. What's the y value? Here's negative 3.
How do you know?
Okay, we're talking limits. So it's as if you have your pencil, right?
Doesn't matter, right?
So here's negative 3. This part here, this part of the line is from the left. this line here is from the right. There's a dot there. I don't care about it at all. Has nothing to do with my limits. Anytime you have a random point, it's not going to tell you anything about limits. You just ignore it because that's just the value. But it tells you nothing about the limit. Do they give you graphs like this? Of course, you know, because they want you to know. You just ignore it and you just look at the parts that are like the continuous path to that, but then I ignore any holes or random points. So what is the y value here? 0. And then from the right, so from the right is 5, and clearly these two are not equal, so we say the limit dne does not exist. Okay. And I prefer the dne, or you can write out does not exist. That's what the AP exam will use.
But you should never
That's
lose
College
your
Board.
time writing that.
Yeah, true. Okay, let's do this last page and then we'll do a little quick stretch break. Okay, exploring non-existent limits. So we kind of did just here, right, when you have different values. But we have another time that you would have non-existent limits, and that is when you have vertical asymptotes. Okay, so let's see. Let's graph. Okay, so let's graph this function. Now, I'll have to review. Remember the rule for vertical asymptotes? Okay, that's horizontal. Okay, so there is a vertical asymptote at x equals 3. We will also review these. These are actually in the next section. Yes, the degrees are the same, right? You have x over x, so it's the ratio of the leading coefficients, which happen to just be 1 over 1. So there's a horizontal here. Now I'm just asking for a sketch, so I don't need lots and lots of points.
It's
Yeah, I have it all summarized.
top right,
Yeah.
bottom left.
So here,
Does that-
okay. So here, so what is the limit from the left of f of x? And what is the limit from the right of f of x? And then what is just the limit without the left or the right hand?
Is it right?
Okay, so from the right, so this one, again, I'm looking, my limits are my y values. So this is increasing without bound. So we can write positive infinity for this one. Sorry, that was the second one. Or you can actually write this does not exist because it's not a real number. It's not a real value. So if I just ask you to find the limit and you write does not exist, it's technically correct. And just so you know, the AP exam will go back and forth between the two. So they'll never have like an infinity for A and does not exist for part C. They'll just have one or the other written down. I do like both because I'll specify so you'll know. The reason I like the infinity is because it actually describes the behavior of the graph, and sometimes that's really important. Does not exist doesn't explain what's going on. As you saw on the previous page, we had just 2 different limits, and so that did not exist. This is a very different type of does not exist, if you will. Okay, so this from the left would be negative infinity, or does not exist, because it's, again, not a real number. And so the limit, now clearly these not only do not exist, but they also don't match up. So we would just say does not exist. That's the only choice for that one. Good? Okay, ignore to refer. I just copied these from your book. But you want to take a minute and do, how about we do this? Go through 40, 42, and 44, and then I'll just, once you finish, just take a quick 5-minute break or so. And then you can describe if they both go up, you can say infinity. Okay, so number 40. So A, we got 5, yes?
Yes.
Good. B, we got 2. And since those are not equal,
Then
It's 2 on the 5.
does not exist. Now, G of negative 4 is 2. That means where is the filled in circle? Okay, 42. We get 3, 3, 3, and P of negative 2 is,
17. It's 3.
okay, 44 is,
1, 1.
okay, great. All right, moving on to 2. Limits involving infinity, that means limits that are approaching infinity or limits that you might get equal to infinity, like we saw with the asymptotes. So this is just a reminder. Remember, it's a symbol. Infinity does not represent a real number. Okay, that's why technically we say the limit doesn't exist if we get infinity. That's used to describe the behavior of a function. Now, what happens when we approach infinity or negative infinity and we get a real number? That tells us about the end behavior. That tells us about the horizontal asymptotes. Does that sound familiar? Okay, so we have to remember these two. It could be one or the other. Here's an example. Usually if you approach positive or negative infinity, you get the same answer. This is like one of those rare cases where we approach from the right. We get 1. And approach negative infinity, we get negative 1. So negative infinity approaches negative 1. Like I said, usually we don't have 2 horizontal asymptotes, but it can happen. So that means we have 2 horizontal asymptotes. They are y equals 1 and negative 1. And make sure you include the y equals because vertical will be x equals. Vertical asymptotes are x equals. Okay. Good so far?
Would you like us to write it y equals 1 and then y equals negative 1, or y equals 1 comma 1?
Either one is fine. As long as you put y equals. Okay. Here we go. Another example. If we have f of x equals 2x minus 1 over the absolute value of x minus 3, what are the limits? We can use graphs or the tables, and we want to identify the horizontal asymptotes. Okay, so what's wrong? What do you think is going to be? Well, tables and graphs. So we're going to go to our calculator. And we want to put in, just make sure.
How do you do the
Okay, so absolute value, yeah, math. Go over to number, and it says ABS, and then it'll give you the absolute value symbol. Minus 3.
On the table, the graph, we have to go back to auto.
Okay, so I'll tell you how I approach. When I have, here's my graph. Now it's really hard to see because I'm approaching infinity, so maybe I want to zoom out. Yeah, you could do zoom. I was already on zoom trig. I probably should have done zoom 6. But if you press, so one way is you could do the trace button and then just keep going over to the right. It'll jump over.
what zoom did you go to?
Yeah.
Never gonna get to.
Did you go to wait?
I'm just tracing right now. I just click the trace button. It keeps the cursor. I'm looking at the limit as x goes to infinity. So I'm moving all the way to the right, continuing to move. Obviously, it's not going to stop. But if you look at your values, already at 51, I'm at 2.1. Now, I like throwing the table because if you have it in there and you have this set to ask, what I like to do is I'll start out with like 10, and I'll put 100, then I'll put 1,000, and again, I'm looking at very large numbers, so 10,000. You know, ignore these other ones, but you see with the table, if you have it in that setting where you can just ask, you can put in 10,000, 100,000, 1 million, and you can see. Now, be careful because, remember, it might come out as 2 eventually if you put in a really, really big number, but then you know that's your limit, right? So we get 2. Now, for part B, we want negative. So instead of positive 10, positive 100, I would just put in negative. So negative 10, negative 100. What are you getting? Second window. And just, so we could see pretty much the same things happening, but instead of positive 2, we get negative 2. Now, because when we took a limit as x approaches infinity or negative infinity, and we got a real number, that makes these two your asymptotes. So y equals 2, and negative 2 are your horizontal asymptotes, based on that. Now, if one of these, let's say as x approaches negative infinity, and you got negative infinity, then that's not an asymptote, right? It's just if you get a real number when you do limits of infinity or negative infinity. Yes. Okay, back here, right here. So,
Oh, it's asking you the horizontal asymptote.
oh, okay. Yeah, what would be your, do you have a vertical asymptote?
Yeah.
At 3 and negative 3. X equals 3. Okay, these are the same exact property of limits that we looked at as x approaches a real number, have the same properties as x approaches positive or negative infinity. Now, remember how we said previously, oops, we just did this one, as x approaches 0 of sine x over x. What was that equal to? 1. That's different than the limit as x approaches infinity of sine x over x. So these are like the two that you need to remember. I should probably put cosine out of that, but that's okay. So what do you think? Think about this for a minute. Think about sine x. Think about that graph. What's the smallest value that you would get out for sine? Negative 1. And what's the largest value? 1. So this has a range. So sine x is going to stay between negative 1 and 1. And what happens with the denominator? As x goes to infinity, the denominator is getting, right, increasingly large without bound towards infinity. So if you have something that's staying between negative 1 and 1, and the bottom is getting really, really big, has to be 0. Okay? So just keep that in mind. So I'm just saying that they're two different limits, but they, for some reason, students sometimes get them switched around. Okay? Also, I'll just put in here, just in case it comes up, if you did the limit as x approaches infinity of cosine x over x, that would also be 0 for the same reasons, because cosine also stays between negative 1 and 1, and then the denominator would go to infinity, and we get 0.
Is there something special about cosine that cosine is sine x over x equals 1? Is cosine x over x?
No, because cosine of 0, is cosine of 0? 1. So you would get 1 over 0, so it's just undefined. Okay. All right, how about these limits? So before you look at these, or maybe you can look at them now, I'm going to give you...
No, wouldn't it be 0 for A because the top is smaller than
Yeah.
the bottom?
Wait, it's
I have an asymptote review.
Look, we got it. What an epic format.
I love it. I mean, I made this one
Yo,
worksheet.
Ryan, did you see that?
What?
Can I
Oh,
say
this is
something?
really hard.
Oh.
Separate the
Yes.
areas.
Don't worry,
So
there's
then
just
it's
hammer right over there.
right?
Yeah.
Got it.
Okay. So I just gave you a handout on reviewing the horizontal asymptotes because again, horizontal asymptotes have to do with the limits as we approach positive and negative infinity. So I have in here, number one, it says if the degree of the numerator is less than the denominator, such as a, then what do we get? Y equals 0 for a horizontal asymptote, or if I'm specifically asking for the limit, we just put 0. Okay, so we're just comparing. We're basically comparing x squared to x to the third. We ignore everything else going on in the problem. We just look at that largest degree, the term with the largest degree. Make sense? How about B? Okay, they're the same, so that is also on here. What's it say? If they're the same, ratio of the leading coefficients, which is 3 over 2. And then, because I made it for my calculus class, I guess I could share it with pre-calculus teachers. Okay, C. What do you think? 3? Okay, so you could separate, if you're not sure, what you could do is separate one of the properties of, you can make this 3x over x plus the limit as x approaches infinity of sine x over x. Ah, what is it? It's 0. So remember, be careful.
No, that's what X
Oh.
approaches 0.
So I said, remember we did this one, but infinity. So it's, yeah.
Let's ask, Miss Casey, I forgot everything I learned in elementary school. Which one's the denominator and which one's
Denominator is,
Okay.
okay. Oh, you know what? I forgot to revise this. There's supposed to be a limit as x goes to infinity here. Sorry. No, I just... Now, what you could do for this one...
Well, oh, this one says degree of numerator and then just denominator.
Oh, where? Did I make a mistake on there?
It says
Ah.
degree of numerator.
Degree of degree. I got a lot of degrees, yeah. One too many there.
And then there's not one on the denominator.
Oh, how did that happen? Okay, I'll look back at that. That's not good. Okay, so here you can split this up into two separate limits. And so I can even split up this one into two separate, but what would be the limit as of 1 over x? As x? So that would be 0 plus 1, it's a constant. So this is 1. All of this is 1 times, now we can consider this one is just a rational function and it's just 4. So we get 4. Okay. Am I going too fast?
Wait, how do you get 4?
Because 0 times 1 equals 4.
That's
Times 1
wrong
times
and
4
makes no
equals 4.
sense.
It's okay, we knew what you meant. Thanks.
I did
The degree of the top and the bottom are the same, so 4.
Oh, this sheet.
This is 0.
I don't know how you got the 1.
This goes to 0 here.
So that's under one of the 0 and the 5, right?
This goes to 0.
It goes to 0.
X on the bottom is not 0.
Okay.
Can you do the top two? Or scroll up? How do you,
Okay.
It's just D. I just don't know how you got 1.
So I can take this and even separate that. Now break up each part. 1 over x as x goes to infinity goes to 0. And this is the limit of a constant, which we just said was,
1.
that's how we got 0 plus 1 in the first.
Isn't it there's the one where the infinity is the limit of a constant? Where the one is on the bottom?
No, if this is a constant, it doesn't matter what this is.
Oh,
All right, now, these are going to be our vertical asymptotes. Okay. It doesn't say that, but basically when you're looking at getting values of infinity and negative infinity, which I have kind of labeled down here, that's also on that sheet that I gave you, then you know it's going to be a vertical asymptote. So if you get an answer of infinity or negative infinity, that's a vertical asymptote. So here we have limit as x approaches 2 from the left of x over x minus 2. So we're going to use graphs and tables to find the limit. So let's take a look at the A. So we have x over x minus 2. Oh, I forgot to change my graph.
Well, it's actually pretty good.
It doesn't matter, because I could see 2 from the left. I could see enough. 2 from the left goes to negative infinity. And then the next one,
It's a different one. What's into it?
did you do greatest integer function last year?
oh, right.
Then we'll skip it.
I didn't.
Don't worry about it. I'd only do it if you guys covered
Wait,
it, but
did you just like Matt? What happened? It changed. Oh, you scrolled down.
I scrolled down.
It's the answer to
So what the greatest, you guys don't need to know it for calculus, but the greatest integer function will take, usually you see it in brackets. So for example, the way you read it is the greatest integer less than or equal to this. It's just like 2. So imagine if you were on a number line, if you just looked at the integer to the left. So if I put 2.9, it's still 2. This is 2. But as soon as I go, I could even put 2.999. I still have 2. So what you also might hear this called the step function. It's like a bunch of steps and then it just jumps up. So you have these little line segments. And but don't worry about it. Okay, vertical asymptote. So on that paper that I gave you steps to finding the vertical asymptotes, right? So first thing we want to do is simplify it, that we look at the denominator and set it equal to 0. You always want to remember that step of simplifying in case there's a removable discontinuity. So here we go. This one, we look to factor it. Now the numerator factors, but it's kind of irrelevant in terms of the denominator because nothing will cancel. So I have a vertical asymptote at x equals -2. Okay, so we found the vertical asymptote. By the way, I didn't ask, but does this have any horizontal asymptotes? No, because the numerator's got a larger degree than the denominator. Now I want to describe the behavior to the left and the right of each vertical. So that means I want to look at 2 from the left. Oops. You're right, negative. So since we already know these are vertical asymptotes, we know that they're going to be either both positive or negative infinity, or one of each. Sometimes, just so you know, you could get both positive infinity for both of them. Like 1 over x squared is an example, but they both go to positive infinity at 0. from the left. Did you look at your graph?
7 over.
Yeah, you can also kind of plug in numbers too, if that helps to figure out.
Then the first one's.
What do you think? Negative infinity for the first one or positive infinity?
Wait, from the left.
From the left?
I mean, all I know is
Because this is square.
f of -3.
Not negative.
Oh,
Oh, yeah. And from the right, it's a.
Oh, duh, Steve, no. That's what it is.
Which one?
I put the equation and I got it.
So from the left, negative infinity, from the right, positive?
Look,
Yeah.
positive.
So
Yeah.
whenever it says describe the behavior, that's what we're looking for here. Okay?
So that's described behavior.
Yeah, this is describing the behavior.
What's the behavior?
And
Vertical asymptote.
the
I abbreviate whenever possible.
You say the time.
Okay. All right, how about the next one? Does the denominator factor?
yeah.
Yeah. 2x plus 1 and x minus. Okay. Does anything cancel? No. So now I have two vertical asymptotes. I have x equals -1/2 and x equals 3. So I have, unfortunately, 4 limits to consider this time. Basically, for each asymptote, you have 2 limits. It takes longer just to write it than to actually look at your graph. So we'll type this one in. What's that? Let's see. So you should see 2, well, you're not going to see the asymptotes, but see what's going on. So here's your -1/2 and here's your 3. So from -1/2 from the left goes positive, so it's positive and negative. So this will be positive infinity, negative infinity. And then what about the other one?
Negative.
And then the next, so from the left it is, wait, what was it? From the left it's positive.
Left is positive, right?
Yeah. Good.
Are we finishing this whole chapter?
Not the chapter, just 2-1 and 2-2. We have time.
Yeah, no.
We're good.
I was
We're good
just
on
wondering.
time. So if we finish early, we finish early. Ooh. I don't want to make any promises yet.
For 2 pages.
I know. What do we have? 12:59. We got
Oh, sorry.
20 minutes for 2 pages. We got this. Okay. Actually, and this is the easy. I think this is the easiest part of the section. And behavior.
Oh.
So, but in behavior, all you have to do is look at the largest term at the top and the largest term at the bottom, and basically reduce it. Okay. So, what you want? Well, you could do that. They're just saying that in limit notation. But take these 3 graphs. We want to match them with its end behavior. So we don't care what's happening in the middle. We just care, this one goes up to the left and down to the right. This one goes up to the left, up to the right, and this one's down to the left, down to the right. So I want to take this term and this term. And what do we get? We get 3x squared. We don't care about anything else because end behavior only has to do with limits as x goes to infinity. So all we care about that largest term.
So it's B.
B. Okay. How about number 2? So we want this one. And we do want to pull coefficients along, okay? So any kind of negatives out in front, any coefficients, numbers that are out there. So this one becomes what? A negative 1/2 x to the third. Now, we know what x to the third looks like. If you put a negative sign, it just switches it, right? Okay? You agree?
Process of elimination.
Yeah. Just to double check, we will just put x to the third over negative x. We do get negative x squared, which we can confirm is. All right. Okay. So this one. Find a power function and behavior model. So I kind of walked you through that in that last example. We didn't call it that, but that's what it is. Here, imagine there's nothing in the denominator, it's just a 1. So my power function and behavior model would be, well, what's my largest degree? Negative 2x squared. And that's it.
This is a long name, power function. And
I know. It just describes. Here, what is it going to be here? Y equals 3. And that also happens to be a horizontal asymptote. This one didn't have a horizontal asymptote, right? Because it's just a polynomial. Good.
Oh man, we're on.
oh, there's a group activity?
Yeah, I think I might just.
Oh.
Yeah, that's good.
If you really want to do it, it's just more
I
examples.
really don't want to do it.
Okay,
I hate
this is kind of a, this is a tricky, sometimes this is hard for some students to see. If you have something that's difficult to investigate as x goes to infinity or negative infinity, you can take the reciprocal, or the reciprocal composition of f of 1 over x versus x, f of
What
x.
does that word?
Here's an example. So think of let's just look at 1 over x. And you'll see why. So let's look at y equals 1 over x. What does that look like? It's like this and this, right? So if I want to investigate the limit as x approaches infinity of 1 over x, okay, what do we... So this, another way to investigate this would be 0 from the right of x. So these two, approaching infinity of 1 over x, you can take the reciprocal. So approaching infinity and approaching 0 from the right will give us the same results if you take the reciprocal. And what are these both equal? No, I'm not saying you have to always use this because sometimes I think it might be easier just to look at this and we know that goes to 0. And then if you look at limit as x approaches negative infinity of 1 over x, that's actually going to be the same as approaching 0 from the left of x. So you can always take the reciprocal of something and just, instead of approaching infinity, you approach 0 from the right, and if you approach negative infinity, you can change that to 0 from the left and take the reciprocal. This one, so if I want to find limit as x approaches infinity of sine of 1 over x, that I can change to be approaching 0 from the right of sine x. Because we know what does sine x look like, right? It goes through 0. So from the left, or sorry, from the right, as x approaches 0 from the right of sine x, that's 0. And then we could do the same thing for negative infinity.
Also zero.
Yeah. Yeah, from the left side. Which it doesn't matter because we know the sine curve, right? Right. From the left versus from the right, it goes through 0. Now,